Hello everyone! In this lesson you will learn about security features and requirements on hash functions. This lesson will cover one-way functions, hash collisions, avalanche effect, and discuss the evolution of security estimates for hash functions. Hash functions appropriate for use in cryptographic applications are designed with some specific qualities in mind. To make it as difficult as possible to work back to find out what the input was, to make the outputs be uniformly distributed over the space of all possible outputs of that length, to avoid two different inputs producing the same output. Not all hash functions have to be cryptographic. Many applications like verification of checksums of downloaded files just need short fingerprints of data that are computed efficiently and reasonably well distributed, but do not require a guarantee of security. Some applications may also be memory or performance critical rather than security critical. Cryptographic hashes are generally more sophisticated computationally and might be slower for that reason. This lecture will cover the main requirements on hash functions intended for use specifically in cryptographic protocols. Cryptographic hash functions must be one-way functions. A one-way function f is easy to compute for any input x, but given a specific output value y, it is computationally infeasible to find any input x such that f of x equals to y, that is, to invert f. It is not yet formally proven that one-way functions actually exist, but at the current state of modern cryptography, they are widely believed to exist with respect to reasonable and practical definitions of easy and computationally infeasible. An example of such function is x cubed modulo n, where n is the product of two randomly chosen large primes and the factorization of n is unknown. Computing f is a relatively simple thing to do, but to reverse the procedure is much more difficult. That is, given a reminder, to find the value x that was originally raised to the third power. This procedure is referred to as the computation of modular cube root with modulus n. If the factors of n are unknown and large, this is a difficult problem for which no efficient non-quantum algorithm is known. However, if the factors of n are known, then there is an efficient algorithm for computing modular cube roots. Here is an example of x cubed modulo n for a small n. Here n equals to 143. Let's build a table of some values of x and see what the result of computation of f would be. Inverting f, that is, finding a modular cube root with modulus n, is computationally equivalent to factorization of n. In this simple case, integer factorization of n is known. It's 11 by 13. That means that this is not a one-way function, because inverting any result of f easily gives possible options for x, simply with solve. And all the solutions suggested by solve do in fact produce the same expected output. However, already for a 500-bit long n, inverting x cubed modulo n, or factoring n, would take decades on a multi-core personal computer, making it computationally infeasible for a regular adversary to attempt. Like this specific example, stops after 30 seconds of trying. Finding an input to a cryptographic hash function that corresponds to a particular output should be at least as difficult as factoring the preceding number. This property is also called pre-image resistance. That means for essentially all outputs, it is hard to find any input that hashes to that specific output. In the preceding example, the function produces the same result for a set of different inputs. Such set of inputs is called a collision. For a cryptographic hash function, it should be computationally infeasible to find another input that has the same output as any given input. Try for yourself a few guesses to find a collision for SHA-256 hash function. This property of hash function is called second pre-image resistance, or alternatively, weak collision resistance. Imagine an attack trying to break second pre-image resistance as asking random people when they were born until you find someone who shares your birthday. Strong collision resistance, on the other hand, is the infeasibility of finding a pair of any two inputs that hash to the same output. An attack looking to break strong collision resistance would work similarly to writing down everyone's birthday in a group until you find any match. Let's try some for SHA-256. Note that by definition given in the previous lecture, hash functions take an arbitrarily long finite input and produce a fixed-sized output, so they map from an infinitely large space of inputs into a much smaller space of possible outputs. This means that collisions will always exist. However, collisions should be hard to find and essentially never occur in practice. Another important and desirable feature of a good hash function is the non-correlation of input and output, or the so-called avalanche effect, which means that a small change in the input results in a significant change in the output, making it statistically indistinguishable from random. A hash function demonstrates the avalanche effect if a single flipped bit in the input causes a change of on average half the bits of the output. This example examines if the Keccak-256 hash function has this property. To create inputs to the hash that differ in one single bit, let's define a function that will help us flip a random bit in an integer. And use this function to create a pair of integers that differ by just one bit. To observe the avalanche effect on a large number of inputs, generate a list of 10,000 random 256-bit integers and create such a pair for every integer. Make sure that the Hamming distance is exactly 1 for each pair of integers, which means they differ in 1 bit. To perform hashing on the actual bits of the inputs, you will need to turn each integer into a byte array, and hash the pairs of byte arrays with Keccak-256. Compute the Hamming distance for each pair of outputs, that is, in how many bits they differ, and compute the mean of the Hamming distances between all the hashed outputs. The mean value of approximately 128 here shows that one changed bit on the input, on average, causes a change of 128 bits in the 256-bit output. If you were comparing pairs of random integers, the Hamming distances would be roughly 128 on average. This means that the Keccak-256 hash function scrambles its inputs very effectively, so that the input and the output do not correlate. To illustrate this, calculate the standard deviation and plot the probability density function of the distribution of the results. You can see that it matches a normal distribution with the mean around 128. When a hash function is said to be cryptographically secure, it is important to understand that such an honor is a temporary one, though perhaps it may remain intact for decades. For instance, MD5 was designed to be a cryptographic hash function satisfying all the aforementioned requirements and remained one for about 15 years, until research showed ways to easily and quickly find and generate collision. One famous collision is these two quite long inputs. These two sequences look almost identical to the human eye, and indeed, they differ in only 5 bytes out of 128. But despite being different, they produce the same MD5 hash. And many such collisions were then published, along with the ways to programmatically generate a collision to any given input. As a result, MD5 is no longer considered a cryptographically secure hash function and will only be used to detect unintentional corruption, such as an incompletely downloaded file, but not intentional forgery.